Here's a question that sounds like it has an obvious answer, and the obvious answer is wrong. Take two identical containers of water, one hot, one cold, and put them in the freezer at the same time. Common sense says the cold one wins, since the hot one has to cool all the way down before it can even start freezing. But under the right conditions, the hot water freezes first. And after 60 years of scientists poking at this exact problem, nobody can fully agree on why or even whether it's real. This puzzle has a name, the Mpemba effect, after a Tanzanian student named Erasto Mpemba. In 1963, Mpemba was making ice cream for a school project. Students were supposed to boil a cream and sugar mixture, let it cool, then freeze it. Worried he'd lose his spot in the shared freezer, Mpemba skipped the cooling step and shoved his still hot mixture straight in. When he checked an hour and a half later, his had frozen solid. His classmates' cooled mixtures had not. His physics teacher told him that was impossible. Mpemba didn't let it go, and years later he tracked down a physics professor named Dennis Osborne who agreed to actually test it. They ran the experiment with water instead of cream, got the same strange result, and published it. The effect got Mpemba's name attached to it, even though he was nowhere near the first person to notice. Aristotle wrote about it around 340 BCE, describing water that had already been warmed as cooling faster than water that started cold. Francis Bacon made a nearly identical claim centuries later. Descartes wrote about it too in an essay on meteorology, so this isn't some fringe modern claim. People have been reporting it for over 2,000 years. The hard part isn't finding people who've seen it, it's explaining it. Researchers have floated at least 5 separate mechanisms, and none of them fully hold up on their own. The first is frost. In a frosty freezer, a container of cold water sits on a layer of frost that stays frozen and insulating. A container of warm water melts that frost underneath it, creating a thin layer of liquid that conducts heat away much faster. That's a real effect, but experimenters who insulate the base of their containers from the freezer floor still sometimes see hot water win, so frost can't be the whole story. The second is dissolved gas. Cold water holds more dissolved gas than warm water. As warm water cools back down, gas redissolves into it, and that process actually releases heat, which should slow cooling rather than speed it up, so this one mostly muddies the picture rather than explaining it. The third is supercooling. Water doesn't always freeze right at 0 degrees Celsius. It can drop several degrees below that before ice actually starts forming. Because freezing needs a nucleation point, some impurity or air bubble to get started. Some experiments suggest that water which started out warmer supercools less and starts freezing sooner as a result. But this effect depends on things as small as a speck of dust in the container, which is part of why it's nearly impossible to reproduce, even in the same lab using the same equipment on different days. The fourth is evaporation. Hot water loses more molecules to evaporation as it cools, leaving less water behind to freeze. Measured mass loss from evaporation, though, is usually under 3%, which isn't nearly enough to explain the size of the effect people report, and the effect has still shown up in sealed containers, where evaporation isn't even a factor. The fifth is convection. Water cools from its surface and its edges first, so the coldest water sinks and warmer water rises to replace it, creating a circulating current. Water that starts out hotter develops much stronger convection currents, and those currents can keep it losing heat faster even after it reaches the same average temperature as the water that started cold. In 2012, the Royal Society of Chemistry got so many competing claims about which mechanism was correct that they opened a public competition for the best explanation. They received over 22,000 submissions. There still wasn't a clear winner. Then in 2016, a tightly controlled study tried to settle it for good. The researchers found no evidence that warm water cooled to freezing faster than cold water. If anything, warm water took measurably longer, which is exactly what basic thermodynamics predicts. But here's the strange part. When they moved the temperature sensor by just 1 centimeter inside the container, a small Mpemba-like effect appeared out of nowhere. When they went back and checked older studies that claimed to observe the effect, the reported differences were often within the margin of error created by exactly that kind of sensor placement. That doesn't necessarily mean 2,000 years of observations were all wrong. Freezing water is far messier and more variable than most people assume, with dozens of small factors, impurities, container shape, sensor position, air currents, all capable of shifting the result. Controlling every single one of them at once turns out to be much harder than it sounds. And there's a reason it might matter more than it seems. If hot water genuinely does freeze faster under truly identical conditions, that would mean water molecules somehow retain information about their previous temperature, a kind of thermal memory that current physics doesn't account for. Proving that would mean rewriting a piece of thermodynamics that has stood for over a century, so maybe it's worth being a little relieved that, at least under the most careful testing so far, water still seems to just follow the rules.